In the last video, we talked about this idea of the electric flux, but there was a crucial assumption we had been making the whole time. We had assumed the electric field was uniform the entire time, and that was an assumption under all of the formulas we ended up working with. But we can easily find ourselves in situations where the E field isn't uniform. So what do we do then? What is the flux through this surface here if the electric field through the surface is not constant? We can't just willy-nilly use the same formula we came up with in the previous video. While we might know A, the area, what do we choose for the electric field? It's not so obvious which, if any of these field vectors, deserves to be the chosen one.
But I am the chosen one. Okay, sorry.
So a useful thing we can do now is define a vector that's already perpendicular to the area. This vector is typically called, very creatively I must say, the area vector. Its magnitude is given by whatever the size of the area is in the appropriate units, and its direction is given by the fact that it's perpendicular to the area itself. Now, just applying a little reverse engineering here, if we happen to choose any of the electric fields here, we may write the product EA cosine of theta as the vector E dotted with the vector A. This is known as the scalar product between the vectors E and A, otherwise known as the dot product. Taking two generic vectors, we say A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Another way of looking at it is A dot B is the magnitude of the projection of B onto A times the magnitude of A. Or symmetrically, you could think of it as the magnitude of the projection of A onto B times the magnitude of B. In any event, what we have here is E dot A, again where we just chose a random E. But we can't really call E dot A here the flux going through the entire area element because the electric field changes throughout the element. So the key here is to shrink this area element into something much smaller, so small that it's an infinitesimal area element, dA. Now the flux through this tiny area element is E dotted with dA, the new tiny area vector. Keep in mind, we're not saying dE, we're not making the electric field infinitesimal. We can't change the electric field, it's just given to us. We're just making the area really, really small. That's what's in our control. The area is in our control. Provided the area is actually small enough and the electric field changes smoothly throughout the area, then the flux through this small element is just given by E dot dA. If you now wanted the flux through this entire surface, you would have to integrate the flux over each individual area element. Now I know what you're thinking, sheesh, easier said than done, man. I'm not about to integrate something complicated like that. I get it. We can run into many situations where actually trying to evaluate this integral is practically hopeless. But let's try it here. Imagine the electric field here is given by 2j hat plus negative 4x plus 5 k hat, and we're asked to find the flux over this square surface with dimensions of 1 meter on each side. I'm going to be sloppy with the units here, but just imagine for now that all of the distances are in meters and the electric field is in newtons per coulomb, for instance. The electric field isn't constant, so again we have to integrate over tiny dAs like we said. We see that the vector dA just has the magnitude of dA and points in the z direction, or the k hat direction. So the vector dA is the magnitude dA times k hat. Then evaluating the dot product between this and the electric field leaves only the k hat components, because another way the dot product works is the way you see on the screen here. Normally we would have to evaluate this as a double integral, but luckily this problem is simple enough for us to consider it as a single integral. If, for example, we imagine an infinitesimally thin sliver, we only have to integrate this sliver along a single dimension, namely the y dimension. Since the sliver is just a rectangle, its area is equal to 1 meter times the differential distance dy. The reason this is okay to do is the electric field is constant along this whole sliver. We can't really make a sliver in the other direction because the electric field isn't constant along that direction. And now that we've set up the integral, all we have to do is evaluate it and we're done. This then is the flux through this sheet here, and we calculated it using integration. Now all this talk about flux, and we still haven't even mentioned Gauss's law. On the surface, Gauss's law looks quite complicated and daunting. Like, hold on, there's two integral symbols, and what is that oval thingy that connects them, and what is S? This right here is actually a formal definition of it, or it's one formal definition at least. We're going to take this formality and completely ignore it in the basics section. So rather than introducing Gauss's law as what it actually is, why don't we imagine a simpler looking version? We'll define all the variables in a second, but I want to stress to you that really there is a profoundly deep level of simplicity in using Gauss's law. All this time we've been talking about open surfaces, like the area in the previous video and this one here. But Gauss's law only applies to closed surfaces. This little circle here indicates that we have to be integrating the flux along a closed surface. For our purposes, a surface is a closed surface if, like with this cube or sphere here, we can clearly delineate an inside of the surface from the outside. So now if we have a closed surface like this spherical surface here, and it encloses some amount of charge, then Gauss's law states that the electric flux through this closed surface is proportional to the charge inside the surface by a factor of 1 over epsilon naught. We see spots of positive flux here where the electric field is popping out of the sphere. And here are some areas of negative electric flux, where the electric field is sinking into the sphere. Kind of interesting and pretty cool, but how does any of this help us? How do we use this new problem-solving tool? We'll explore the implications in the next video.